Here is my short presentation of my past and my present research. Okay, so here we start from my PhD work. So I will briefly introduce my PhD work, what I have done. So during my PhD, I focus on the discontinuous percolation transition. Basically, we search for the new models and developing scaling theories. The phase transition can be classified into two different. So one is the first order transition, another is the second order type transition. So in the first order type transition, which involves the discontinuity change in the order parameter, where in the second order transition, which is continuous. I have studied on various percolation model, which is starting from the two parameter random growth percolation model and nucleation and preferential growth model and random growth lattice filling models. So I conducted the finite size scaling study on this percolation model to understand the transition from continuous to discontinuous percolation. So all this work, foundation of my current, even my recent research work to explore the phase transition and critical phenomena in various complex systems. So what is percolation? Percolation is a type of geometrical phase transition where the system changes from disconnected to connected phase at critical threshold. So depending on the occupation probability, you can see from this three picture, for a particular value of occupation probability, system can connect it to opposite edge. And there are many such examples of percolations. So how can we characterize the percolation transition? So all these critical exponents and the morphology of the percolation cluster and all derived geometrical quantities which describes the behavior near percolation threshold and which found to be universal and independent of percolation model or the lattice structure. This slide shows key equation and graphs illustrating this concept, including the percolation threshold at PC and on the 2D square lattice. Though percolation is well known to be a second order continuous transition, however, in 2009, people claimed a discontinuous percolation transition on random graph model and also in the 2D square lattice and others. According to their model, instead of placing the seeds or the links or the bonds randomly, they use some modified growth rule. And depending on their rule, they try to suppress the growth of the largest cluster and they enhance the growth of the smallest cluster. And if you follow the rule, then you can see the transition with a delayed threshold, with a high concentration and a abrupt jump of the order parameter, and they claim to be a first order. Now here we describe our models. So for the two parameter percolation model with constant growth, so here we use two basic algorithm of percolation. One is Hossain-Kappelman algorithm. According to Hossain-Kappelman algorithm, we distributed the seed throughout the empty lattice and which form the small cluster which different size, and now empty peripheral site of each and every clusters will call for occupation with certain probability, with growth probability following the Leith algorithm. And once a site is rejected, and it will be rejected throughout the simulation time. So from this two parameter constant growth model, what we get, our estimated critical exponents are same as ordinary percolation and all the geometrical quantities follows the finite size scaling and the order parameter shows a singular distributions. So the models belongs to the semi-university class and there is no discontinuous percolation transition. So we need to extend this suppressive cluster growth model. Okay, to look for the first order transition, we need some preferential growth instead of the constant growth. So here we use some growth model. For this growth model, the single cluster grow with the highest probability and the largest cluster grow with the smallest probability. And if you do that, then you can see the significant change in their cluster morphology. For smaller value of rho and the highest growth, higher growth probability, you can see a compact largest cluster with the absence of the finite cluster inside the cluster. Okay, what we get from this model? So from this phase diagram, for each and every initial seed concentration, we estimate the critical growth probability And one can see that for smaller value of critical initial seed concentration, the higher value of growth, critical growth probability higher than the ordinary percolation. And we also estimate the critical exponents, and the right part of these exponents values are same as the ordinary percolation, and intermediate it's deviated from the percolation, and from the left side it's equals to the space dimension, which is some sort of the first order transition. And for the Binder cumulant, for the higher values of initial seed concentration, there is a crossing for different system, but there is no crossing for the smaller seed concentration. Now for the order parameter distribution, if we go from large seed concentration to smaller seed concentration, one can see a single arm distribution to a broadening of distribution, now a two bimodal distribution, and peak to peak distance are increased with increase of system size. And we also derived another phase diagram taking care of the two peak to peak distance. Now we can see that from the right side one single phase to double phase and double coexisting phase, and we claim that this is the first order transition in percolation. Here we introduce another percolation model, which is a lattice filling model. So in this model, each and every time step, Monte Carlo time step, there will be a one nucleation center. The green one is the nucleation center, and every time step, the existing nucleation center grow with their neighbor particle with some growth probability. And once a site is called for occupation and it's rejected, and it will be rejected throughout the time step, only I put one restrictions. So if two cluster merge, they will never grow. So this is frozen cluster. So if you do that, then you can see and if you track the size of the largest cluster, then there you can see a significant jump in the order parameter, which is considered to be first order transition. Now we estimate the critical exponents and their critical area fraction, and we draw the phase diagram. In the middle figure, you can see the most left side of the dotted line is the continuous transition, and it belongs to the same university class, and most right side of the dotted line it shows the discontinuous transition, and intermediate time scale it shows the percolation with different university class. Okay, during my first postdoc at IIT Bombay, I worked on the active matter systems. We created a different complex active environment, and we tried to characterize their collective behavior by placing a tagged passive particle into it in the complex environment. So in this model, active particle are follow this Langevin dynamics, and whereas Langevin dynamics, and where two particles come closer, they repulse each other with some excluded volume repulsive force, and AP is the self-propulsion speed, and T and eta are the Gaussian white noises as used, and for the passive particle we did not use the self-propulsion speed of the particle. To understand the collective behavior of the complex active environment, we calculate the MSD, and here three plots for the three different concentration of the active particle, and each plot for smaller value of Percolate, you can see it's diffusive throughout the time scale. For if you goes and increase the Percolate, the self-propulsion speed, you can see that for smaller time scale it's diffusive, in the intermediate time scale it's super diffusive, for the large time scales it's diffusive again. Now, if the particles are inside the cluster or in the dense systems, so what will happen? Now you can see the MSD behavior is changes. For the short time scale, it's subdiffusive. In the intermediate time scale, it's super diffusive, and for the long time scale, it's diffusive again. And we also characterize by calculating the autocorrelation function. So here I have done another project which is absorbing polymer at the wall. To design the polymer, we use SSLJ potential. So this is because of to overlap the beads of the polymer each other, to their effective friction should be less, and there will be no interlocking. So here all these polymers or the rods follow this Langevin equation, which consists of spring potential, bending potential, and excluded volume repulsive potential and self-propulsion speed. So what we get from this model, so depending on the Percolate, so you can see the red line is the wall. So if the Percolate is smaller, the self-propulsion speed of the polymers is small, then it's uniformly they are oriented. But if you increase the Percolate, then you can see there is aggregation of polymer at the wall, and they show some different kind of pattern, and we also characterize their pattern. And here we plot the number of particle which is d-weighted particle. There is a transition from d-weighted to weighted and partially weighted, and here we get the power load distribution. So during my short project at IIT Patna, my research focused on how we can extract the oil from the porous medium by using deep eutectic solvent. Deep eutectic solvent is a particular mixture of choline chloride with urea or choline chloride with ethylene. And for the porous medium, we use two different surfaces, silicon dioxide and graphite. And for this molecular dynamics, we use the GROMAC software for the simulation, and we try to characterize the affinity of the solvent with the surface and the molecular structure. Now in my current position in Japan, my research focuses on how to derive the hydrodynamic equation from the particle dynamics of active matter systems. So when we have a collection of large number of active particle, and sometimes it shows some interesting collective phenomena like swarming, modality induced phase separation, flocking. And when we talk about the large scale collective behavior, then microscopic details of the systems is less important. We need to know the hydrodynamic equation to know about the collective behavior of the system. To derive the hydrodynamic equation, here we use two basic model in active matter physics. One is the Vichek model. In this Vichek model, all the particles move with the speed v0, and their orientation is considered their average orientation of its neighbor particle, and here the eta plays an important role which perturbs their orientation. And if you change the orientation, their global parameter, which is the orientation, which is decreasing if you increase the noise, and it dies out at certain critical values. And in this model, the flocking is the universal collective phenomena. So in this BSEC model, as I told you, that noise plays an important role. So here we use the different noise from small value to higher value, that we can capture all possible dynamics of the system. And here also we use two different parameters as a coarse graining parameter, which is along the time and along the space. So now here we use another model, which is active Brownian particle model. Already I stated before. So in this model, what we get, so depending on the Percolation or the self-propulsion speed, we can get different kind of dynamic of the system. And in this model, so memes, the modality in space separation are the universal phenomena and universal collective phenomena. And from this phase diagram, you can see, depending on the Percolation, we can go from the single phase to coexisting dense and dilute phase. As I said, the Percolation is an important parameter for this model. Here we use different Percolation and the different time scale and spatial resolutions for the coarse graining. So people are already derived the hydrodynamic equation analytically from the continuum description. And in their model, mostly it's based on the symmetries and minimum way to break the equilibrium condition. So derive the hydrodynamic equation from the particle in the macroscopic level is difficult because there is no ground truth model, and we don't know that hydrodynamic descriptions correct up to which length scale and which time scale, and we need to spatial and temporal coarse graining and derive the PD in the closed form, and we don't know about the noise, how we can use and incorporate in our model, and what kind of physical period is necessary for that estimation. Here is the brief overview our method to derive the hydrodynamic equation. First, we collect the data from the particle simulation, and then we need to know which are the hydrodynamic variables. So here we consider the density and the polarity density are our hydrodynamic variables, and we transform it a continuum field by using some Gaussian kernel, and then we use the coarse graining along the space and along the time. And now we use SINDy, and for this SINDy, so we first derive the linear equation, and in this matrix form, the left side is the time derivative of the field data, and the in the intermediate matrix is the dictionary terms, all possible selected dictionary terms which follows the conservations and symmetries, and right side is the parameter. Now we need to reduce the number of dictionary terms by using the sparse regression to derive the hydrodynamic equations. To eliminate the dictionary terms using the sparse regression process, so we estimate the error each and every iterative time step, where error is nothing but the square root of the difference between the predicted value and the actual value. So here you can see for each and every iterative time step, the error is, there is a flat plateau, and when you eliminating one by one, and after that you can find it start deviating from, and we consider that this is the optimal number of dictionary terms. So for the density field and for the polarity field and for the polarity dependent, density dependent polarity field, we choose the different of dictionary terms which respect the symmetries and the holds the conservation's law. In a BSEC model, error for the density field, we get single dictionary terms which is the divergence of P, and this is very relevant to the BSEC model because the density flux dominated by the flow of the active particle for this model, and the coefficient which I derived estimated, so which is close to the coefficient for the estimated from the Boltzmann equation. And the hydrodynamic equation for the polarity density, here we get the advection term and as well as the polar order term. And here the coefficient of grad rho, which is same as the estimated value from the Boltzmann equation. And from the Berg term, we can also get the transient dynamics from this equation. By using this equation and the polarity, the dotted lines are the polarity, and you can get for particular value of the eta, the polarities vanish, and for the smaller value of eta, there is always a finite value of polarity. So at least we can, and all the red crosses points are the simulation data. Though it is not quantitatively matched, but qualitatively at least we can show the phase diagram. We get the hydrodynamic equation for the density field, which consists of advection term, bulk term, surface term, and non-gradient terms. And we found the minimum error, which is at the very large length scale and intermediate time scale. Whereas for the polarity density, there is error is always a high. Actually, polar density is slaved by the density of the system. So therefore, polarity density is not a hydrodynamic variables. So we need to know some dictionary terms which depends on the density, and we estimated few dictionary terms from depending on the density for the polarity density field. From the estimated hydrodynamic equation, if we replace the P with respect to that what we estimated from the second equation, and then we get the negative diffusion, which characterizes the phase coexistence of the systems, basically the memes. After getting the free energy function and estimated parameter value, coefficient value, we also derive the phase diagram. Here the dotted lines are the simulation, and the solid state line for the derived hydrodynamic equation parameter value. And here also we get the single phase to double phase line. Though it is not quantitatively matched, but qualitatively at least we can show the phase diagram for this model. Last but not the least, in my future research, I aim to apply the concept of phase transition and the system connectivity to the biological models, and by using the advanced computational technique like Monte Carlo finite size scaling, I will explore the structural organization in a biological system. Additionally, I will use bridge the microscopic particle behavior with macroscopic continuum model, focusing on the active matter and the hydrodynamic equation. This interdisciplinary approach will uncover the universal principles of self-propelled particle behavior and their application in biological and soft matter physics. Thank you very much.